Glutamate, the brain's main excitatory signal and the foundation of learning. When people think about neurotransmitters, glutamate is rarely mentioned. It is not linked to happiness. It is not linked to motivation. And it does not have the cultural reputation of dopamine or serotonin. Yet glutamate is the most important excitatory neurotransmitter in the human brain. Without glutamate, there would be no learning, no memory, no perception, and no conscious thought. In many ways, glutamate is the chemical language of the cortex itself. To understand how the brain works, we must understand glutamate. The story of glutamate begins earlier than most people realize. In the early 20th century, scientists knew that glutamic acid was present in the brain, but they assumed it was simply a metabolic substance. It was abundant, so it seemed unlikely to be a neurotransmitter. At the time, researchers believed that neurotransmitters had to be rare and specialized. This assumption delayed the recognition of glutamate's true role. It was not until the 1950s and 1960s that researchers began to show that glutamate could directly excite neurons. By the 1980s, glutamate was firmly established as the brain's primary excitatory neurotransmitter. Today, it is understood that the vast majority of fast communication between neurons in the brain depends on glutamate. So what is glutamate? Glutamate is the main chemical signal neurons use to activate other neurons. When glutamate is released, it increases the likelihood that the receiving neuron will fire. In simple terms, glutamate makes neural activity happen. Every thought, every perception, every memory, and every decision relies on glutamate-driven signaling. If dopamine tells the brain what to pursue and acetylcholine sharpens processing, glutamate is the signal that carries the information itself. Glutamate is absolutely central to learning and memory. One of the most important discoveries in neuroscience is long-term potentiation. Long-term potentiation refers to the strengthening of synaptic connections after repeated activation. This process depends heavily on glutamate receptors, especially NMDA and AMPA receptors. When glutamate repeatedly activates a synapse, the connection becomes stronger and more efficient. This is how experiences leave physical traces in the brain. This is how learning happens. This is how memories are formed. The hippocampus, a brain structure essential for forming new memories, is densely packed with glutamate receptors. When glutamate signaling is disrupted in the hippocampus, memory formation suffers. This is why glutamate is often described as the molecular basis of learning. Without glutamate, the brain cannot store new information effectively. Glutamate is also essential for perception. Sensory information from the eyes, ears, and skin is transmitted through glutamate-based pathways. When you see, hear, or feel something, glutamate is carrying that information across neural circuits. Your experience of the world depends on glutamate-driven communication. Even complex mental imagery relies on glutamate activity within the cortex. Glutamate also plays a role in movement. Motor commands from the brain to the spinal cord rely on excitatory glutamate signals. While acetylcholine activates muscles directly, glutamate helps plan, initiate, and coordinate movement at higher levels of the nervous system. Without glutamate, movement would be poorly organized and imprecise. Here are 5 everyday examples of glutamate at work. First, when you learn a new fact, glutamate helps strengthen the synaptic connections that store that information. Second, when you recognize a face, glutamate allows visual information to flow rapidly through the cortex. Third, when you practice a skill, repeated glutamate signaling reshapes neural circuits to improve performance. Fourth, when you focus on a complex problem, glutamate activity supports sustained cortical processing. Fifth, when you recall a memory, Glutamate helps reactivate the neural patterns associated with that experience. Because glutamate is so powerful, it must be carefully regulated. Too little glutamate activity leads to cognitive impairment and reduced consciousness. Too much glutamate activity can be toxic. This is known as excitotoxicity. Excessive glutamate release can overstimulate neurons, leading to cell damage or death. Excitotoxicity is implicated in conditions such as stroke, traumatic brain injury, and some neurodegenerative diseases. This shows that glutamate is essential, but potentially dangerous if uncontrolled. Glutamate is also closely balanced with another neurotransmitter, GABA. While glutamate excites neurons, GABA inhibits them. Healthy brain function depends on a balance between excitation and inhibition. Too much excitation leads to seizures and overstimulation. Too much inhibition leads to sluggish thinking and reduced responsiveness. The brain constantly adjusts glutamate and GABA activity to maintain stability. There are several important facts about glutamate that are often misunderstood. Glutamate is involved in nearly all fast brain communication. Most neurons in the cortex use glutamate as their primary neurotransmitter. Glutamate acts on multiple receptor types, each with different effects and time courses. Glutamate is essential for plasticity, the brain's ability to change with experience. Disruptions to glutamate signaling are linked to conditions such as epilepsy, schizophrenia, depression, and neurodegeneration. So, what is the big picture? Glutamate is not about pleasure, motivation, or mood. It is about information. It is the primary signal that allows neurons to communicate, learn, and adapt. It is the foundation of memory, perception, and thought itself. If dopamine provides drive, and acetylcholine provides clarity, glutamate provides content. Without glutamate, the brain would be silent. And understanding glutamate is essential for understanding how the mind is built from neural activity.
If you enjoyed our channel, please click subscribe.